guys, and welcome back to my channel, Adisa Talks. So today we're going to be talking about optical transducers, and that includes optical sensors as well as optical spectroscopy. So let's get started. Now, a good way to kind of understand optical sensors and optical spectroscopy is to understand the basic electromagnetic wave theory. And light is a form of electromagnetic wave that consists of oscillating electrical and magnetic fields. Now, the electric and magnetic fields of the propagating light are actually perpendicular to each other and to the direction of the propagation. Now, this basic theory kind of includes different laws as well as equations, such as Maxwell's equations, Faraday's law, Ampere's law, Gauss's law, to be able to determine the behavior of light. And it uses also the wave equation, which describes the different forms of the light wave propagation. From there, the phasor notation can also be determined, which is actually determining the amplitude and the phase of the propagating light. Now, there's also interference, polarization, incidence, and the reflection of light that could also be determined to kind of understand this basic theory. Now, interference is actually categorized as either destructive as well as maybe constructive, and it actually determines the different magnetic and phase of the summation of two different waves. In terms of polarization, incidence, as well as the reflection of light, the surface in the incoming beam kind of defines the plane of incidence, and that plane of incidence encompasses the incoming beam and the surface normal and the reflected beam. From there, the angle of incidence as well as the angle of reflection can also be determined. Now, adding the different bounding conditions of this propagating light, you can also determine Fresnel's equation. Now, let's jump into different sensors. There are different sensors that exist out there, but first, let's talk about wave-based molecular sensors. Now, the wave-based molecular sensors use light to determine molecular sensors, and these wave-based molecular sensors are actually optical molecular sensors that are based on light waveguides to basically design, guide, and to confine lights. Now, some of the optical principles and measurement techniques that are very well established and are valuable for designing a molecular sensor are the transmission of light over multi-scale distances in different medias or solutions, establishing a secure communication, as well as maybe fabricating a miniaturized version of the optical and optoelectronic device. Now, the three different types of waveguide sensors are slab waveguides, rectangular waveguides, as well as circular waveguides. Now, slab waveguides use a planar geometry, and they're actually fabricated with a thin transparent film on a substrate with an increased refractory index that can guide light waves by a total internal reflection. And with these sensors, the top surface is usually used as a sensing site. And one of the advantages of using slab waveguides, which have a planar structure, is that it includes an easier fabrication as well as a large sensing site. Now, with rectangular waveguides, these use rectangular cross sections, and they're actually etched out of a substrate, where other types are actually buried in the etched grooves. So with these sensors, they're often used for measurements that utilize interferometry or optical resonation, where the path lengths have to be strictly confined to control interference. Last but not least, circular waveguides are actually the most common form of light waveguides that are used for optical communication. And the advantage to using those is their capability to be used as a probe, where one end of a fiber is used as a sensing site, and the fiber tip can be brought into the sensing site in situ or in vivo for measuring different applications. So, the most fundamental principle behind guided light waves is a total internal reflection, where light is confined in a medium with a high refractory index. And to kind of design the most efficient waveguide, we need to kind of focus on different characteristics of the propagating light, such as the electromagnetic wave, which are described by the Maxwell's equation, as well as the electromagnetic wave equation. But another thing that we should also keep in mind is the important concept behind this guided waves optics, and those are modes. And these modes are actually solutions, actually eigensolutions, to the wave equations for specific wavelengths and polarization with the boundary conditions given by the properties of the materials and interfaces. So, in order to kind of couple the light from a free space into a waveguide, techniques to match wave numbers need to be introduced. And light coupling is a process that is used to match wave numbers of two different medias. Now, there are three types or three ways to kind of couple light to a planar waveguides, and these are gratings, prism, and end fire coupling. With gratings, they're actually fabricated on top of the surface, and it actually adds a grating vector to the light wave and can therefore match basically the wave vectors in the waveguides. With prism, you have an optical power that may be coupled into or out of a planar waveguide by use of a prism. And a prism with a higher refractory index comparing to air is placed close to the waveguide surface with a thin air gap in between. Finally, with end-fire coupling, you have light that is actually coupled into the waveguide by directly focusing at one end. So let's dig more into detail on these different types of waveguide-based sensors. So with slab waveguides, they actually take advantage of the large sensing site, which is easily obtained on the top surface of the waveguide layer. And they mostly utilize fluorescence excitation by an evanescence field, which is induced on the surface. Now, there are actually different configurations, and those different configurations could be used for coupling excitation light into the waveguide, coupling fluorescence back into the waveguide, and the detection of the fluorescence signals. Now, the different applications that are associated with these type of sensors are basically for bacterial sensing, and they've also been designed as an immunosensor for the diagnosis of different pathologies and utilize antibody and antigen binding on the waveguide surface. Now, some of the examples of sensors that have actually been developed is basically an output grating coupler for direct immunosensing, as well as a multiple analyte immunoassay using a silicone oxynitride integrated optical waveguide. Now, let's talk about rectangular waveguides. They're also called channel waveguides, and they do have a different shape compared to the slab waveguides. The one advantage is that it is possible to precisely kind of define the light path length, so it can be easily utilized for different applications based on the optical interference. And an example of a researcher that actually designed a rectangular waveguide for biological application is Mark Zender. And he actually designed a waveguide based on an interferometer for biosensing, where the injection of stropoavidin solution was actually measured. Another important method for channel waveguides is the use of a silicone ring oscillator, and it is typically consists of a straight waveguide coupled to a ring-shaped waveguide that functions as an optical resonator. And so many researchers have actually studied this structure in the hope of kind of using it for an optical logic device that can be integrated in silicone chips. And so another important application area that this sensor could be used in is molecular sensing. So with circular waveguides, which are also called optical waveguides, they possess a cylindrical geometry and therefore have a surrounding material of a uniform refractory index, as opposed to basically potentially multiple refractory indices as seen in planar waveguides. Now, there are two types of modes that could be used. There's a single mode fibers, which are generally constructed for the purpose of like sending energy or information through long distances, and those have a small diameter core which only lets a single mode to exist. But with multiple fibers, they're actually generally meant for information sent over shorter distances. Now, examples of actually sensors that have used this type of design are the hollow fiber sensor, which is a type of sensor that utilizes optical fibers as miniature probe microscope, used for measuring the changes in molecular concentration. And another variation of this type of fiber sensor include the optical fiber chemical sensors. Another type of sensors or optical sensors are surface plasmon resonance sensors. Now, maybe some of you know or don't know, but the focus of recent studies on nanophotonics is to better understand and utilize the different properties of surface plasmons, which are oscillations coupled with metal and dielectric interfaces. And so, using surface plasmon has enabled the use of distinguishable kind of optical phenomena, not only for molecular sensors, but also for different emerging nanodevices, such as nano antennas, nano grating couplers, and plasmonic near-field scanning optical microscopy. Now, in surface plasmon resonance sensors, surface electromagnetic waves that propagate in a direction that is parallel to the metal are called surface plasmon polaritons. And since they propagate along the interface as a wave, they're sometimes called surface plasmon waves. Now, to kind of describe the properties of surface plasmon, we use an intuitive approach and treat each material as a homogeneous continuum, which is described by a frequency-dependent dielectric constant and a dispersion relation, which contains most of the important information about the wave propagation in the structure. So there are kind of two ways to examine how light radiation is coupled to the surface plasmon resonance. And the two configurations are the auto configuration and the Kretschmann consideration. Now, the auto configuration is when a thin metal film is positioned close to the prism wall so that an evanescence wave can interact with the plasma waves on the surface and hence kind of excite the plasmons. With the Kretschmann configuration, the metal film is evaporated onto the glass block and the light illuminates the glass block and an evanescence wave kind of penetrate through the metal film, and so the plasmon are excited at the outer side of the film. So, as you know, these sensors are used for molecular sensing. But for molecular sensing, the surface of the dielectric layer is kind of functionalized with recognizing elements such as antibodies or DNAs. And the metals that are commonly used for the surface plasmon resonance systems are either gold or silver, which are actually suitable for biomolecule functionalization. Now, with surface plasmon resonance, the measurements that we can actually extract from there is the reflectivity curves for the p-polarized as well as the s-polarized radiation of the gold and the silver films. And so examples that have actually been used around researchers that include SPR is a polydimethyl siloxane fluidic device that actually contains an array of micro chambers. And each of these chambers kind of contain a gold spot which is designed for SPR measurements. And so another approach is basically utilizing nanostructures when it comes to surface plasmon resonance. And as you can even think, because this area has been studied, another topic of interest in the study of SPR has been localized surface plasmon resonance spectroscopy of triangular silver nanoparticles. And this technique actually utilized localized surface plasmon resonance in nanoscale metal patterns in order to detect maybe different molecules or maybe different antigens, or antibodies. So let's jump into talking about optical spectroscopy. Now, there are different types of optical spectroscopy, but let's start with absorption spectroscopy. Now, absorption spectroscopy kind of measures absorption of radiation. And from there, we can actually measure the optical density, the transmittance, as well as the absorption spectrum. But the absorption spectrum is a very important quantitative measure to kind of evaluate the optical properties of different solutions. And it kind of provides several types of information, such as the concentration of the solute, the shapes or the size of the suspended materials or particles, as well as the different biological activities that could be happening. And to kind of describe the linear relationship between the absorbance and the concentration of an absorbing species is through Beer-Lambert's law. So one interesting application of absorption measurement for biomedical sensing is optical oximetry. And it is a method that kind of monitors hemoglobin saturation in patients. And the practical technique used in optical oximetry is pulse oximetry, where pulsing absorbance change due to the heartbeat is kind of measured at different wavelengths. Now, a simple implementation of finding the ratio between the hemoglobin and the oxyhemoglobin contents are comparing the absorbance at different wavelengths or two different wavelengths, namely red and infrared. And a typical form of pulse oximetry is with a small device that actually clips at the fingertip, where each side of the clip is either an LED or a detector. Now, as we know, the majority of glucose sensors are electrochemical sensors based on the measurement of the reducing properties of glucose. But using, for example, absorption spectroscopy, there could be a different advantage to that method, such as, for example, several problems relating to blood drawing may be thrown out, and it's very non-invasive, which prevents the patient of pricking himself, hurting himself when drawing blood. So another type of optical spectroscopy is fluorescence spectroscopy. And fluorescence is basically emission of a photon by a substance as a result of an electron transmission from an excited state to a ground state. And fluorescence is utilized for several types of applications, such as lighting, labeling, optical microscopy, chemical sensing, and maybe the analysis of material structures. But there's a diagram that is often used to kind of illustrate the energy levels of a specific molecule, and this diagram is called the Jablonski diagram. And in this diagram, the transition between energy states are actually indicated by arrows, as well as the transition associated with fluorescent excitation or fluorescence emission is indicated by a straight arrow. Now, some of the important features of fluorescence spectroscopy are the Stokes shift, the lifetime, as well as the decay rate of a specific proton. And the Stokes shift is actually defined as the difference in wavelengths between the band maxima of absorption and the fluorescent spectrum. Now, fluorescence spectroscopy could be used for imaging, and in order to do so, we need a microscope. So a fluorescent microscopy is actually a technique where samples are stained with a dye, which is observed with a fluorescent microscope. And some of the essential components, for a microscope are the light source, the excitation filter, the diachronic mirror, and the emission filter. The light source is usually basically a lamp. It could be an Xenon lamp, it could be a mercury lamp, or maybe a tungsten lamp, which has a white band of emission. And so the excitation light kind of passes through the excitation filter, is reflected by the diachronic mirror, and illuminates the sample. And an example or one of the most commonly used dyes is the FITC. Now, another important aspect of fluorescence spectroscopy could be using a quantum dot. Now, a quantum dot is a nanoscale semiconductor crystal where basically the electrons are subject to a three-dimensional quantum confinement. And these are actually fabricated in various forms, and actually, some are integrated on bulk semiconductor devices by lithographic approaches. But for fluorescence spectroscopy, colloidal quantum dots are basically what we're actually interested in because these are chemically synthesized semiconductors nanoparticles. And so as we kind of stated, a quantum dot is a semiconductor, right? And it has a conduction band and a valence band with a band gap, which I kind of spoke about in chapter 4. And the highest occupied molecular orbital is called HOMO, and the lowest unoccupied molecular orbital is called LUMO. And so when these QDs or quantum dots are excited, an electron in the HOMO moves to an orbital in the conduction band, leaving a hole in the highest occupied molecular orbital. And so fluorescence emission is a result of a transition of the electron from the lowest unoccupied molecular orbital back to the highest occupied molecular orbital. And so the emission wavelength is defined by the energy difference between the lowest unoccupied and the highest occupied molecular orbitals. Now, the most significant advantage of using quantum dots is their photostability. Let's talk about light scattering. Now, light scattering is a general category for several different physical phenomena, and it can be considered as the deflection of a ray from a straight path due to irregularities such as small particles or defects. There are basically two types of light scatterings that are important in optical sensing and imaging application, and that is elastic scattering and inelastic scattering. Elastic scattering includes Rayleigh scattering and Mie scattering, and inelastic scattering includes Raman scattering. Rayleigh scattering is a type of scattering by molecules and particle matter that is much smaller than the wavelength, while Mie scattering is the scattering described by the solution to Maxwell's equation for the scattering by an isotropic, homogeneous, dielectric sphere. So the different methods that are based on light scattering, and that includes dark field microscopy, static light scattering, dynamic light scattering, and so forth. Dark field microscopy is a type of microscope that enables microscopic observation of scattered light from the sample. With static light scattering, it's a method that kind of measures the intensity of the scattered light with different measuring angles. And it is basically called static because time average intensity is measured in contrast to basically dynamic scattering where the fluctuation in light intensity are measured. And so that kind of brings us to basically what dynamic light scattering is. And this technique is actually based on the measurement of time domain fluctuation of scattered light intensity. And it is basically used to find the diameters of the suspended particles. Another method that kind of uses light scattering is the laser Doppler velocimetry. And this technique actually measures the velocity of a flow based on the measurement of light scattering that are caused by the particles in the flow. It is basically a non-contact and non-invasive method that can be used for different variety of flow, and that is actually used for molecular sensing as well as to measure blood flow. Another technique that uses light scattering is Raman spectroscopy. And this is a technique that is based on measurement of Raman scattering, which provides information about the vibrational and rotational modes in molecules. Now, in contrast to basically elastic scattering, where the energy is conserved before and after the process, Raman scattering is a process where the incident of light interacts with molecules and some of the energy is lost or increased. Now, this technique can be used for the characterization of diamond films. And so this technique also plays a critical role in characterization of like newly discovered carbon nanomaterials such as graphene or carbon nanotube. And from there, a Raman spectra can also be determined for the single wall carbon nanotubes as well as for graphene. And a subset of basically Raman spectroscopy is surface enhanced Raman spectroscopy. And this technique actually utilizes enhanced Raman scattering of molecules absorbed on surfaces of metal, such as silver or gold. And so, an example of different metals that could be used are actually gold and silver. But when using these metals, those metal nanoparticles can be functionalized to actually detect the specific target molecules. And an example is a PSA, which is a prostate specific antigen, which is actually commonly used as a prostate cancer marker. Also, surface enhanced Raman spectroscopy has also been used for in vivo targeting and detection. And with using gold nanoparticles, they're actually functionalized with the epidermal growth factor receptor and Raman scattering molecules, and are then injected into a mouse that actually bears a tumor for the detection of basically tumor molecules. Now, this technique has also been used in vivo for glucose sensing as well as other tumor detection. I kind of spoke about metal nanoparticles, especially used in Raman spectroscopy, but dark field spectroscopy have utilized metal nanoparticles. Moreover, localized SPR has actually utilized normal metal nanoparticles because they're actually highly sensitive for optical sensing of molecules. Now, metal nanoparticles have actually been made into nanorods, even though it is not possible to find analytic solutions for non-spherical particles with arbitrary shapes. But with nanorod, we're actually able to find analytic solutions for scattering and absorption in those metal nanorods that are being made. Last but not least, let's talk about near-field scanning microscopy. Now, the resolution of a conventional microscope is limited by a diffraction of light called the Fraunhofer diffraction of light. But with near-field scanning optical microscopy, it is actually a type of scanning probe microscopy that overcomes the resolution limit of the conventional microscope by utilizing a sub-wavelength size light source. And this light source, kind of created at the scanning tip, measures maps of the sub-wavelength optical properties as well as nanoscale topography profiles. And the optical resolution of the near-field scanning microscopy is directly related to the size of the light source at the tip, while the capability of topographic measurement relies on the same force sensing scheme as used. So let's summarize the different types of tips that are used in the near-field scanning microscopy. Now, the first type is the aperture-based tip, which is actually the most common type, and it has a nanometer size aperture, which defines the size of the light source. The second type is the metal plasmonic tip, which is integrated with the creating resonator that enhances the intensity of surface plasmon at the metal tip. But last but not least, the functional near-field scanning microscopy tip is integrated with nanoscale quantum dot-based light emitting diodes. And these diodes are actually attached with a small size light emitting element at the tip, and the narrow bandwidth of the quantum dot LEDs provides considerable potential as excitation source for fluorescence imaging. So now I know that was a lot of information and you guys were able to learn a little bit more about waveguide sensors, absorption spectroscopy, light scattering, you name it. So I hope this chapter was a little bit more helpful and kind of helped you and kind of taught you a little bit about optical transducers. And thank you for watching. See you next time. Bye.